Okay, what's going on, folks? It's Mr. Brunsvold here. Today we're going to be taking notes on balancing chemical reactions. I know a lot of you were really confused on the fill in the blank from the lab yesterday. No worries, those are going to be our notes for today, is filling in those blanks. So if you want to go back and change your answers to the lab, that is A-okay. All right, so synthesis reactions. In a synthesis reaction, two reactants, so you can see we've got one reactant, S8, which is sulfur, and one reactant, Fe, which is iron. Two reactants combine to form one product. And so our one product here is iron sulfide. And so then what we're going to do now is balance this reaction. So it's helpful to count the number of atoms on each side whenever you're balancing a reaction. So on the reactant side, we have sulfur and iron, and on the product side, we have sulfur and iron. I count 8 sulfur atoms on the reactant side. I count 1 iron atom on the reactant side. I count 1 sulfur atom on the product side, and I count 1 iron atom on the product side. And we want all the atoms to be the same on both sides of the reaction. This is called the law of conservation of mass. We're going to learn more about that in tomorrow's notes. But the idea is that matter cannot be created or destroyed during a chemical process. And so then for that reason, the number of each kind of atom before and after the reaction needs to be the same. Okay, so we are going to start by balancing out our sulfur atoms because those are uneven, right? We have 8 sulfurs on this side and 1 sulfur on this side. So we're going to do that by putting an 8 in front of iron sulfide. We always put the number in front whenever we're balancing a chemical equation. Whenever we're balancing a chemical formula, we use the subscripts, right? But whenever we're balancing a chemical equation, we use, this is called a coefficient. And that just means that we put a number out front. So now we should have 8 irons and 8 sulfurs. Change these to 8s. But shoot, now our irons are unbalanced, right? Because we have 8 irons on this side and only 1 iron on this side. So we're going to fix that by putting an 8 over here. And so now we have 8 irons on this side. So we have the same number of sulfurs, the same number of irons. We didn't put a number in front of sulfur on the reactant side, so I'm just going to get rid of that blank. Right? And then that's how we would write that chemical formula. S8 plus 8Fe yields 8FeS. Okay, now I'm going to start going a little bit quicker through these. Next up is a decomposition reaction. In a decomposition reaction, how many reactants do we have? Well, there's just the one right here. So one reactant breaks apart to form 2 products. Okay, so then let's go through the example. We've got, on the reactant side, we've got hydrogen and oxygen. On the product side, we have hydrogen and oxygen. How many reactants do we have? Or of each kind of reactant do we have? Looks like we have 2 hydrogens and 1 oxygen. And on the product side, looks like we have 2 hydrogens and 2 oxygens. So we need to balance out the oxygens. So I'm going to put a 2 in front of the oxygen on this side. Okay, so then now I have 4 hydrogens and 2 oxygens. So the oxygens are balanced now, but now the hydrogens are unbalanced. So I'm going to fix that on the product side by putting a 2 in front of this hydrogen. Now I should have 4 hydrogens total on the product side and the reactant side, and 2 oxygens on the products and reactant side. We're good. So I'm going to get rid of the blank in front of the oxygen, and that is my chemical equation. 2H2O yields 2H2 plus O2. Okay, single replacement reactions. In a single replacement reaction, One reactant is an element, right? So we can see down here our element is zinc. The other reactant is a compound. So we can see down here our compound is copper sulfate. If the element is a metal, so that's what we have down here, our element is zinc and zinc is a metal, it will replace the metal in the compound. And so that's what happened in this reaction. Look, zinc came through and replaced the copper. So now instead of copper sulfate, we have zinc sulfate. And now the copper is the one that's by himself. If the element is a nonmetal, it will replace the nonmetal in the compound. So that should make sense, right? Metals are replacing metals, nonmetals are replacing nonmetals. This one's a really easy example to balance. Why? Well, it's actually already balanced. Look, we have one copper on this side, one copper on this side, one sulfur on this side, one sulfur on this side, four oxygens, one zinc, one zinc. You can get rid of the blanks because this one's already balanced. We don't need any coefficients. In a double replacement reaction, the products and reactants are all compounds, right? We don't see any elements here. But what kind of compounds are these all? Well, they all have one metal and one nonmetal, or at least they all have one metal and at least one nonmetal. So here we've got lead with a nonmetal, we've got potassium with a nonmetal, potassium with a nonmetal, lead with a nonmetal. So when you have metal and nonmetal, remember that that is ionic. So the products and reactants are all ionic compounds. A double replacement reaction, they don't have to be ionic compounds. You can do a double replacement with covalent compounds as well. But most of the ones that we're going to see are ionic. Okay. And so the nonmetals from one reactant will replace the nonmetal from the other reactant. So that's what we see happening down here. Look, the NO3 that was paired with lead is going to replace the iodine. So now the NO3 is paired with potassium, and the iodine is now paired with lead. This was the bright yellow reaction from yesterday. Oh man, sorry, I think I'm starting to get sick. Hopefully you don't catch anything through the WebEx. All right. Reactants. So a lot of reactants and products in this one. So we can see we've got lead, we've got nitrate. I decided to keep nitrate together because that's a polyatomic ion. I don't know if I've said this to you, but polyatomic ions aren't going to break apart in the reactions that we're doing. Potassium and iodine. And same thing on the product side. Okay, so let's count how many. Looks like one lead. Looks like two nitrates. One potassium, one iodine. One lead. One nitrate. One potassium. Two iodides. Okay, so now let's start to balance this example, because you can see we've got an uneven number of nitrates and an uneven number of iodides. So let's start by balancing the nitrates. Got two on this side, one on this side, so I'm going to put a 2 in front of potassium nitrate, and that will make it so that I now have 2 nitrates, but I also have 2 potassiums now. So now the nitrates are balanced, but now the potassiums and the iodides are unbalanced. And you can see we've got 2 of each on this side and 1 of each on this side. So I'm going to fix both of those by putting a 2 in front here. That's going to make it so that I now have 2 potassiums and 2 iodides. And then everything should be balanced now. One lead, one 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, 2 iodides, 2 iodides. And so then I'm going to get rid of the blanks in front of lead nitrate and lead iodide. And we should see that this is now balanced. Okay, last one. Combustion reactions. These are the cool ones. In a combustion reactions, one of the reactants is always oxygen. So you can see that from the list that I gave you yesterday. One of the reactants is always oxygen, O2. And then the other reactants, we call that a fuel. And combustion also require heat. And so in the reaction yesterday, that was provided by the lighter. So just real quick, some of you might be familiar with the fire triangle. To create a fire, you always need 3 things: oxygen, fuel, heat. Sometimes it's called, instead of heat, it's called an ignition source or a spark or something like that. But the idea is you can never make a fire without those 3 things. They all need to be present. So you can't make a fire in a vacuum because there's no oxygen. Obviously, you can't make a fire if you don't have anything that's going to burn. And usually you need some sort of heat to get the fire started. Where am I? Right here. Okay, so let's balance this one out. So on each side we have carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. To start off, we have 1 carbon, we have 4 hydrogens, and 2 oxygens on the reactant side. On the product side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Now, this one's not going to be too difficult to balance. Some of these combustion reactions are a real pain to balance. I'm just going to warn you. These are, I think, the toughest ones to balance in general. And so just be wary of that. So to begin with, our carbons are balanced. So we'll move on to hydrogen. Here we have 4 hydrogens on this side, 2 hydrogens on this side. So we'll balance that by putting a 2 here. So then now we have 4 hydrogens here. But now we're up to 4 oxygens. And so now we need to balance out our oxygens. We have 4 oxygens on this side, 2 oxygens on this side. So we're going to put a 2 out front. And then now we have 4 oxygens, so everything should be balanced. We can get rid of our blanks in front of methane and carbon dioxide. Oh, whoops, forgot to do that. So yeah, I would get rid of the blanks in front of here and here normally. Okay, so what are your instructions for today's assignment? You're going to balance the reaction on the next slides. Classify each reaction as a synthesis reaction, a decomposition reaction, a single replacement, a double replacement, or a combustion reaction. And some of these reactions might fit into more than one classification, just so you know. So if it does fit into more than one classification, try to get both of them if you can, or at least get one. Okay, and that's all I got for you today, folks. So hopefully this makes sense. And if you have any questions, let me know.